Welcome everyone, and thank you for tuning into this session. Whether you're a data science enthusiast, a student, or a professional looking to brush up your knowledge, you're in the right place. In today's video, we are going to demystify one of the most foundational algorithms in machine learning, logistic regression. We'll be diving into one of the most widely used algorithms in machine learning. Logistic regression is not only a classification tool, but also forms the foundation for more complex models, from medical diagnosis and spam detection to predicting customer churn. Logistic regression has diverse applications. We'll go from the basics to advanced concepts, ensuring you understand both the theory and practical application of logistic regression. Now let us understand what logistic regression is all about. Logistic regression is a supervised learning algorithm mainly used for classification problems. Despite having regression in its name, it's typically used for categorical outcomes. Think of yes or no, 0 or 1, true or false labels. Unlike linear regression, which is meant to predict continuous values, logistic regression predicts a probability between 0 and 1. In this session, we'll not only cover binary classification, but also extend the concept to multiclass classification and performance metrics used to evaluate the model accuracy. By the end of this presentation, you'll have a good understanding of how logistic regression works and how to apply it to solve real-world problems. Before we dive into how logistic regression solves the classification problems, let's discuss why linear regression isn't the right tool for the job. First, linear regression doesn't limit the output between 0 and 1. So when you're trying to predict probabilities for classification, you could end up with values like minus 0.5 or 1.3, which are nonsensical in a probability context. Second, linear regression is sensitive to outliers. If a dataset contains extreme values, these outliers will disproportionately affect the best fit line, making predictions less reliable. Finally, classification requires a clear decision boundary between classes and linear regression does not provide such a boundary effectively. This is why we need a different approach, which leads us to logistic regression. So how does logistic regression fix these issues? It uses the Sigmoid function, which causes the output to fall between 0 and 1. This transformation makes it perfect for classification tasks where we need to interpret outputs as probabilities. The Sigmoid function converts any real valued number into a probability. The closer the output is to 1, the more likely the instance belongs to the positive class, and the closer to 0 means it belongs to negative class. We also apply a threshold of 0.5 to decide the predicted class. If the probability is greater than or equal to 0.5, the prediction is 1, positive class. Otherwise, it is 0, that is negative class. This allows us to make more intuitive and interpretable predictions. The core of logistic regression lies in the hypothesis function, which is defined as h of x is equal to 1 upon 1 plus e to the power minus z, where z is theta naught plus theta 1 x1 plus theta 2 x2 ... and it extends to theta and xn. It is a linear combination of input features. This is our sigmoid function. The sigmoid function h of x ensures that the output lies between 0 and 1. This formula allows us to model the relationship between the independent variable and the probability of a certain event happening. The closer h of x is to 1, the more confident the model is that the sample belongs to the positive class 1. And the closer it is to 0, the more confident it is that the sample belongs to the negative class 0. In linear regression, we minimize the mean squared error, that is MSE, to find the best fitting line. But for logistic regression, we need a different approach. We use logistic loss function, also called as binary cross entropy loss, to evaluate the accuracy of the model. This cost function penalizes predictions that are wrong, especially when the model is confident but incorrect. The formula for this cost function is cos h theta of x is equal to minus 1 by m summation of d, where y is the actual class and h theta x is the predicted probability. This cost function is then minimized using optimization algorithms like gradient descent. Now that we understand the theory behind logistic regression, we need to evaluate its performance. In classification tasks, simply looking at accuracy isn't enough. We need to evaluate how well the model distinguishes between different classes. This is where metrics like precision, recall, and F1 comes in. These metrics helps us understand the model's strengths and weaknesses, especially in cases where a class imbalance exists or when the cost of false positive or false negative is high. In the next few slides, we will discuss each metric in detail. Let us start with confusion metrics, which is a great way to understand how your classification model is performing. A confusion matrix breaks down predictions into four parts. The confusion matrix contains four key components. True positive, the number of correct positive predictions. True negatives, the number of correct negative predictions. False positive, the number of incorrect positive predictions. And false negatives, the number of incorrect negative predictions. These values helps us calculate performance metrics like precision, recall, and the F1 score. Think of it as a performance report card of your model. The cleaner the confusion matrix, that is more true positives and true negatives, the better your model is doing at classifying the instances correctly. Accuracy is one of the basic metrics. It tells us the overall correctness of the model. It is defined as the ratio of correct predictions, both true positive and true negatives, to the total number of predictions. The formula for accuracy is equal to TP plus TN. That is true positive plus true negatives, whole upon sum of true positive plus true negative plus false negatives. Accuracy is a great metric when the classes are balanced, but it can be misleading when there is a class imbalance, as a model can achieve high accuracy by predicting the majority class correctly while neglecting the minority class. Precision. Next we have precision, which focuses on the positive class. It is the ratio of correctly predicted positives to the total predicted positives. It measures how many of these instances predicted as positives are actually positive. Precision is especially important in situations where false positives are costly, such as predicting whether a person has a disease. The formula for precision is equal to true positive whole upon true positive plus false positive. High precision indicates that when the model predicts a positive class, it's usually correct. If we predict someone has a disease, we want to be confident. That's where precision matters. Recall, on the other hand, focuses on how many of the actual positive instances were correctly identified by the model. Recall is crucial when the cost of the missing positive class, or that is false negative, is high. For example, in fraud detection, missing a fraudulent transaction could be extremely costly. The formula for recall is equal to true positive upon true positive plus false negative. High recall means the model is capturing most of the positive instances, but it may come at the cost of lower precision. The F1 score is the harmonic mean of precision and recall. It gives you a single number to summarize both metrics and is especially useful when you need a balance between precision and recall. The formula for F1 score is F1 is equal to 2 times precision into recall, or upon sum of precision plus recall. However, sometimes you might want to prioritize one over the other. That's where F beta score comes in. It's a generalization of the F1 score that allows you to adjust the balance between precision and recall based on your needs. For example, a beta of 2 gives more weight to recall, while the beta of 0.5 puts more emphasis on precision. Logistic regression is used in many practical scenarios across different industries. In healthcare, it can predict the likelihood of a patient having a disease, given a set of symptoms. In finance, it is used for credit scoring, helping banks assess the risk of loan applicants. In marketing, logistic regression is commonly used for churn prediction, that is determining whether a customer will leave or stay. It is also used in spam detection, customer segmentation, sentiment analysis, and click-through rate predictions for online advertisements. Its simplicity and interpretability makes it the go-to model in situations where interpretability is as important as predictive power. While logistic regression works well for binary classification, what if we need to classify more than 2 classes? This is where one versus test, that is OVR, comes in. In OVR, we train one classifier per class, treating that class as the positive class and all other classes as negative. The model then predicts the class with the highest probability. This model extends logistic regression to multi-class problems, allowing you to handle datasets with more than 2 categories. To summarize, logistic regression is a powerful and widely used tool for binary and multi-class classification. It models the probability of a class using a sigmoid function and is optimized using a loss function. We discussed key concepts like hypothesis function, cost function, performance metrics, and its real-world application. Whether you are solving problems in healthcare, finance, or marketing, logistic regression provides a solid starting point for many machine learning classification tasks. Thank you for your time today. If you have any questions, feel free to reach out. If you found value in this, feel free to connect with me on LinkedIn and subscribe to my YouTube channel. Let's continue learning and growing together. Thanks for watching and happy learning.